Hello everyone, I'm Haoxin and I'm glad to present our recent work with you. The presentation will include background, motivation, our solution, preliminary evaluation, and conclusion. As we all know, software such as computers and smartphones are everywhere and they usually contain bugs. An urgent problem that has been actively studied is how to improve the quality of software. Effective way to reach the goal is software testing, and symbolic execution is one of the most popular ones. Traditional SE engine work as follows. It first collects the source code of the software system under test and then transfer the source code into an intermediate representation, so-called IR. Then the SE engine analyzes the IR instruction to find any potential errors. Notably, during the analyze, the major operation is to do the interpretation, which analyzes all the instructions. It's no doubt that such checking can be time-consuming, carry out the severe performance issue. To mitigate this issue, two major types of studies are devoted to speeding up the SE engines. The first one is compiler optimization-based approaches, and the second one is focused on reducing path exploration and speeding up constraint solving for fast SE. Although these approaches are effective, they did not consider that interpreting alone can have performance downsides. In summary, the remained performance issue and the limitations in existing SE engine motivated us to design a new solution to mitigate the problem of how can we reduce interpreting overheads for faster SE. Therefore, we propose a tool FastKLEE in this study. Two key insights are behind our design. First, the number of interpreted instructions tend to be huge, with usually several billions only in 1 hour long. Second, a large portion of pointers in C can be statically verified to be type safe, and reducing the bound checking of redundant ones can accelerate the execution. This insight is inspired by the type inference system in C. That means same as the safe or unsafe pointers. The instruction during interpretation can also be classified to be safe or unsafe as well. Then we can avoid the unnecessary bound checking of safe interpreted ones to reduce overheads. Based on the above insights, we designed our solution. We kept the general workflow of traditional SE we just mentioned. We designed two new phases to support our approach. In the first phase, we introduced a type inference system to classify instruction types, where unsafe instructions will be stored in a checking list. Then in the second phase, during interpretation, we conduct a customized instruction operation that only checks those unsafe instructions to avoid redundant checking. In this way, FastKLEE could help reduce interpreting overhead for faster symbol execution. We also evaluated the effectiveness of FastKLEE. FastKLEE is implemented upon KLEE and CCQ and evaluated over core utils datasets. Particularly, we use the metric speedups to measure the time spent on exploring the same number of instructions and apply the following simple formula to calculate the speedups. Here is the results. The axis represents the 40 test programs and the ordinate represents the speedups. We could observe that our approach can reduce by up to 5.1% time as the SOTA approach. Well, please allow me to give a summary of this work. We present a FastKLEE to reduce the interpretation overheads for faster symbol execution. In future work, we are actively pursuing exploring more valuable execution paths in software system. Here, our key insight is that if one path contains more unsafe instructions, the path is more likely to be vulnerable or exploitable. Okay, That's all about my presentation. Thank you very much.